going to talk about synthetic fuels past, present, and future. Okay?
Okay, thank you very much. Thank you for allowing us to participate in this seminar. Past, present, and future. Well, obviously we're not the past, and we're currently not the present either. However, we look to the future, and to be an important part of the future of FP and synthetic fuels. What I'm going to talk about, I'm going to do a little bit of background that probably most of you are very familiar with anyway. Why are we working on synthetic fuels? What's the importance there? And then we'll talk a little bit about microchannels. Microchannel technology is our particular approach to a variety of chemical processes, including synthetic fuel production. Then we'll talk a little bit about the past, which you, again, are probably fairly familiar with, where Fischer-Tropsch chemistry came from. And then we'll talk a little bit about what's going on today. And again, the other speakers have done a very fine job, and a much better job than I could do, in telling you what's going on in coal to liquids, gas to liquids R&D. And then we'll talk a little bit about the future, about various conversion technologies, but particularly about our technology and how we see our technology fitting into the future of synthetic fuels. Synthetic fuels, why are people interested in synthetic fuels? I think you all know this. High oil prices. Oil prices go up and down. Many of you remember in the late 1990s when oil prices were $10 a barrel. Well, that's not true anymore. Oil prices have gone up. The important thing is, it's predicted that oil prices will stay relatively high for quite some time. I think we heard one of our speakers today say that they would stay between $59 and $100 a barrel for the next 20 years. And that's probably a fairly good estimate. Another thing is a concern about peak oil. That is, in the U.S. at least, the oil fields that we have, for example, the North Slope and other places, have really gone past their prime and are declining. And so we're looking to have energy sources within the U.S. that are potentially longer term and can reach out further into the future. Energy security, about 60% of U.S. fuel is imported, as everyone knows, a lot of it from the Middle East and elsewhere. But we could use domestic coal and biomass to meet our goal. The goal in the U.S. is to produce about 2.3 million barrels per day by 2017. I think this was announced by Congress, of synthetic fuels, one of the targets. Infrastructure. In order to utilize the current infrastructure, it would be best to use fuels that are compatible with the current infrastructure. And so diesel fuel, gasoline, etc., obviously fit that bill better than some of the other fuels that people are thinking about. What are these synthetic fuels? Where do they come from? These are replacements for oil, or actually additives to oil in some cases, as the previous speaker mentioned, and others. They can be derived from gas, natural gas, gas to liquids. Been studied quite a bit. You heard about Shell, you heard about Sasol, you heard about others. Coal to liquids, again, this is something where the United States has a very large supply of coal that could last us hundreds of years into the future. And several other countries around the world, in particular China and Russia, have large deposits of coal that could also help supply fuel out into the future. Biomass to liquids, this is kind of the hot area currently, certainly in the political spectrum, because it impacts a very large number of regions of the U.S., and a lot of different companies imagine they could be players in this. This is certainly a source of energy that could be tapped and could add significantly to the fuel in the future. And then waste products. This has been attempted several places where they use municipal waste, and it's still a possibility, and there are probably certain niches where each of these technologies, each of these routes will be useful. Most of these processes have 3 steps. The first step is a syngas generation step, followed by Fischer-Tropsch, although some people have other options for that, and then a hydrocracking to get the appropriate product. Again, as our previous speaker did a nice job of defining what that product should be for a particular application. Let me talk now about microchannel technology. And this is our approach to doing a variety of chemical processes, but in particular today I'm going to talk about how we apply it to Fischer-Tropsch and a little bit about natural gas. What are microchannels? Microchannels are very narrow grooves or slots in a metal device that allow you to get a variety of advantages compared to conventional technology. You're all familiar with how conventional reactors are operated, fairly large tubes, or in some cases, slurries and so on, gigantic structures that have fluid flowing through them, and they can be packed with a catalyst. And these are typically a few inches to maybe as much as 6 or 8 inches across. And the limiting feature of the chemistry in these tubes, of course, is how fast you can get things to the surface of the tube, in particular heat in and out. Most of these processes are very exothermic or very endothermic. And so the distance from the center of that tube, which is going to be the hottest or coldest spot, to the wall is really very important. Now in microchannel technology, the typical dimensions for our microchannels, and this is a cross-section of a small device that we were operating in the laboratory, shows you a variety of different types of microchannels. And the typical dimensions on these are on the order of 1 millimeter or less in terms of the shortest distance from one wall to another. That's what we call the gap. And the reason that's important is that the distance from the center of the channel to the wall is the longest distance that a molecule has to travel to touch the wall, for example, to meet up with a catalyst, if it's a coated catalyst, or for heat to transfer from that fluid to the wall, or for heat to be transferred into the fluid, depending on what process you're in. But this is sort of a typical cross-section of a microchannel reactor. The microchannels run into the screen here, and they can be anywhere from a few inches to several feet long in reactors that we've studied. So the major improvement is increase in heat and mass transport in these reactors. Well, that didn't work out so good. Process intensification. What does this allow you to do? If you make a stack of these microchannels and you have a different process going on in the 2 different channels that are next to each other, one of them, for example, an exothermic reaction like this combustion reaction. This is in fact how we operate our steam reformer, is we have a combustion reaction in one channel and we have the steam reforming process in this other channel. The reaction rates and the resonance times that you can get in here are much shorter. Resonance times are much shorter, therefore the reaction rates need to be much higher and can be much higher than in conventional systems. And so the resonance time in the reactor can be 10 to 100 or even more lower than it is in a conventional system. And this leads to a number of interesting observations. The distance, the gap in this channel is on the order of 1 millimeter or less. And again, that's important because the shorter is that distance, the faster is the heat transfer, the higher is the heat transfer, and the mass transport that you can get out of this process. And the heat fluxes that we've measured in several of our reactions are much, much higher than you can get in a conventional tubular reactor, sometimes on the order of 100 times higher. Some of the advantages of microchannels, it depends on the specific application. We're looking at oxidations and reductions, and Fischer-Tropsch, steam reforming, a variety of things. One of them is reduced capital costs. Since these reactors have very, very high rates, the reactors are small, so they have small footprints. And since they're made not stick-built on site, but are made prefabricated and moved to the site, they can be deployed fairly rapidly. And this is one of the applications that we're looking at for the DoD that I'll mention later on. Lower feedstock and operating costs. There's high efficiency, especially thermal efficiency in these reactors. And so you can get better conversions, better selectivities. We've demonstrated that in a few reactions. Improved energy efficiency. There are energy recuperators within the microchannel reactors. Typically there's a heat exchange zone followed by a reaction zone to get very good heat integration. Reduced emissions, for example, for a steam reformer. In our combustion process, which is a catalyzed process on the one side of the wall, the peak temperature is much, much lower than it is a conventional reformer where you have an open flame and you generate a fair amount of NOx. We generate almost no NOx. Decreased downtime. In a sense, we have reactors that you can slot one in for another as you would change a valve in a plant. You can go and change a reactor, take one out, fix that one, and put a new reactor in. They're modular and they can replace one another. And then they're inherently safer, and this is important more for oxidation reactions, because the size of the channels themselves is on the order of the size of the quench diameter of the process. And so they act like quench devices, flame arresters, if you will, and stop a lot of radical reactions. there's some inherent safety, especially for those oxidation reactions. Let's look a little bit at the past, though I think you know this already. Well, that didn't all come out, did it? Well, I didn't make these slides. These were made by our development department. There's supposed to be a map of the world on here, and obviously it's pointing to where these guys are from in Germany. That's where Fischer-Tropsch developed, as all of you probably know already, in the 20s. This group was looking at a variety of high-pressure reactions of nitrogen and hydrogen and carbon monoxide and other things. And they hit on this reaction that made this waxy material. And then they used that during World War II to produce fuels. And also, they produced as much as 124,000 barrels per day in World War II, which is a fair amount, considering what was going on then. And then, obviously, you know about Sasol and some of the great things that have gone on there. For a variety of reasons, they've been producing synthetic fuels in South Africa from coal and from natural gas using their FT technology, which is basically the gold standard currently. And it uses low-grade coal in the one process at Secunda, which makes a variety of fuels and chemicals. And it's an amazing place to go see if you ever get a chance, because they extract out every possible molecule that's valuable. Okay, what's going on more currently? There's currently about 200,000 barrels per day capacity around the world, and the plant at Secunda is the largest of those. There are some new ones going in, as you know. There are a variety of world-scale plants that have been announced. The Sasol Chevron, Shell, Oryx plant, or some of these are under construction. Oryx, as someone mentioned, is already bound to produce and transport the first fuel. And there are lower cost processes being developed with a variety of companies. You heard about Rentec today. Centrolium has an active program, and there are many others around the world. We're working on both the steam reforming and the Fischer-Tropsch process, and we think that ultimately our process will have a variety of advantages over other conventional processes, both in terms of efficiency and in terms of portability, applicability to various fuels. This is sort of a summary that one of our guys made up in terms of what's available today in terms of the current syn fuels production. And obviously the Sasol plant is the biggest one, but these are some of the other ones. You know about the Shell plant that's been running for some time, this Oryx plant that is now up and running. There's a fair amount, and you heard about some of the projections for how much synthetic fuel is going to be produced over the next 20 years as this grows fairly rapidly. There have been some developments recently that the guys wanted to mention. There's been some test flights using a GTL blend. I think that may have been using the Sasol fuel. I'm not sure, maybe you can fill us in. But so it's been successfully used in a variety of applications that are important applications, important niche applications. As one of our speakers mentioned, even if all the plants that are planned today come on stream, it's still only going to be a small fraction of the fuel market. And so very likely these fuels will go into the niche applications where you can extract the maximum value. This Oryx plant has started up. Centrolium and Sinopec have signed an agreement to work on both gas and coal-to-liquids in China. And this Pearl project has been launched, and we'll see where that goes. $18 billion sounds like a lot of money to me. But then there's some setbacks, as you heard about ExxonMobil announcing that they're not going to build their plant. And then this shipment from Oryx apparently delayed. The only reason we put that in there is it says that sometimes there's other things beyond the technology and beyond the science that can get in the way. This is apparently from the press, it's a logistics problem. Okay, let me talk about our technology briefly. We've been working on Fischer-Tropsch since about 2001, in fact, even before that. Our company was founded in 2001, and we go back to some work that was done before that at P&L, Pacific Northwest National Labs. And most of our work was done on developing catalysts in small reactors. This is a sort of a typical small reactor. There's a coin here, I don't know if you can see it, but it's a pretty small reactor, not much, it's smaller than you can. And we do a lot of our catalyst development in there using less than a gram of catalyst in most of the activities. And we've been working on trying to develop improved catalysts and running catalysts under some unusual conditions. And that's probably one of the most important things here, is we run our catalysts under very different conditions than conventional technology. Much higher flow rates than conventional technology, much shorter contact times. And this does give you some difference in terms of performance. And then we've now gone to scale this up. And our scaled-up reactor, this is the largest one we've got to date, started up early this year. And it's about 26 odd inches in length. And this is the process channel length. And this is what we expect the commercial process channel length to be. That is, when we go to a commercial reactor, we're basically going to take this block and just reproduce it out towards it, and perhaps in this coolant direction. The process flow is downwards as the syngas comes in on the top. There's catalyst packed in here, and the product comes out the bottom. And there's a coolant, in this case we're just raising steam, goes across. It's a cross-flow reactor. And the way to scale this up, as I mentioned, is we can make this wider in this direction to make the coolant channel longer. But these process channels are very similar to what we think our commercial reactor is going to be. It's going to be not much bigger than this. It'll be longer in this direction and a bit wider in that direction. And this one produces about 2 gallons per day of an FT mixture, typical FT mixture, alpha about 0.9-ish. This is our setup for it. The reactor itself sits up in here, and all this claptrap is just to collect the product, separate things out, condition the gas, and so on. Process length, as I said, is about 0.6 meters. We have 40 microchannels in there on the process side. Coolant length is less than that. We have 420 coolant microchannels because they're much smaller because they're under high pressure. And the capacity is about 8 gallons a day. And we've successfully demonstrated this particular reactor for more than 1,000 hours now. This shows a little bit of the performance data. Unfortunately, I would like to have had more data in here, but this is all they wanted to talk about, really. We were running this at 320 pounds, 215 C average temperature with a 2-to-1 syngas, and a contact time of 560 milliseconds. And these are the data points. These are the conversions of CO, and this is the methane make, which is down around 15% selectivity. And there was some slight decline due to wax buildup, but basically over this time it stayed pretty much the same. Now there's not a lot of points in here, as you see, because we were moving the conditions all around the place. This was not held constant for this 1,200-hour test. It was jumping around. We put it through its paces and did a lot of things as much as we could, given the restrictions of the device, the size, and so on. But it ran very well. Ran for about 1,200 hours. And at the end of that, we regenerated the catalyst and could return it to its initial activity. So we demonstrated we could regenerate the catalyst in situ, which was an important point. This shows where our technology fits into some other conventional technologies, and I've basically stolen this slide or borrowed this contents from a guy from Shell who gave a presentation at CatCon here in Houston 4 years ago. And basically he was talking about the limits of the slurry design versus the packed bed. And naturally, being a packed bed guy, he said that you can't see it very well here, but there's a yellow line here saying what the limit of the Shell technology would be based on the heat removal and the way the catalyst is packed in there and so on. And the slurry design has a much lower limit, and this is in terms of productivity per volume of reactor, because of it's basically filled with wax, so you have less catalyst density. So these are the limits that he came up with based on some calculations, and these are where some of the conventional plants actually fit in. The experiments that we've run in our laboratory, including the one I showed you on the larger device, are out here. We're at about 3 to 4 times, maybe more than that, maybe 8-fold in terms of the actual catalyst activity, in terms of the productivity we can get out of a reactor. And this allows us to do a number of things in terms of shrinking down the process, shrinking down the reactor, shrinking down all the equipment. Where are we headed? As you know, gutter is where a lot of people are building things. There's a lot of work going on there, and you know about that. You may end up out there as well. Cold liquids for a variety of reasons, for energy security and so on. Economies of scale, all of these things are these mega plants, and economy of scale is an important thing in all of the plants that you've heard about from other folks. But our niche is probably a little bit different than that. While we get reasonable economy at large scale, we actually get much improved economy compared to conventional processes at the small scale. We're looking at these small niches, offshore plants, offshore facilities, bio facilities, waste facilities, where you have a very small resource. It's not like a gigantic oil well. It's a small resource where there might be a factory of some sort, or a mill, a paper mill, and the waste from that, we could convert that into fuel. It's a fairly small application. But you require some innovative process technology to fit in there. You can't use these gigantic reactors. They don't scale down well, as somebody mentioned about the hydrocracking. This is what a conventional steam reformer looks like. I'm not going to talk too much about steam reformer, but this is what a conventional steam reformer looks like, with 20 million standard cubic feet per day, 100 by 100 by 100 feet, and it's, as you know, it's capital intensive. This is what our similar capability reactor is going to look like compared to the other one. You can see the picture in there or not, but it's supposed to be a shadow of the picture there. There's basically 4 little units here with a few reactors in each one, capable of producing the same amount of gas as this large plant. There's a 90% reduction in size, about a 30% capital reduction, 100% increase in profit. That's interesting. I hope that's right. I hope it's more than that. Obviously, economics are, fungible. And what is our commercial FT reactor likely to look like? What we see is that, you remember that little reactor that I showed you, the cross-section, that would be this front piece of this, and then we would just multiply that going back through this shell. And the shell would hold a high-pressure inert gas in it, maybe steam, and we would bring the process and the coolant in. The process would run down through this, collect the product to the bottom, and it would come out here. And then we would have the steam run in here and we would go crosswise and maintain pressure on this vessel within this shell. So this gives us a fairly small device with a fairly significant capacity that we could ship around fairly easily. And in fact, one of the main purposes we have for that is for a mobile fuel plant. And again, this was sponsored by the Department of Defense. One of the things they're looking to do is, you may not know that for our battlefield capabilities, 70% of the lifting capacity that they need is used not to transport people, not to transport munitions, to transport fuel. And the fuel comes from the U.S. So they take it to this sandy location to get their fuel there. So what they said, well, wouldn't it be nice to have a plant where there's a lot of natural gas lines around, to hook one up in a fairly stable location to a natural gas line and generate your diesel fuel, your JP8, JP5, whatever they're going to make, in situ near the battlefield, and minimize the risk and the cost and the time associated with transporting that fuel to the battlefield. And so this is the scheme that we've come up with and we've been working on. These are our FT reactors that would fit in here. This is what our steam reformer would look like. And these are the other different pieces, more conventional pieces, so on, that would fit here. We didn't put a is there a hydrocracker in here? No, but you presumably would have a hydrocracker in here as well if you want to make JP8. But each of these pieces would fit into a C5A plane, so you could just fly them in. And the idea is they would assemble these, and it would take about 2 weeks to put all the pieces together, hook it all up, and then you'd be pumping out about 500 barrels per day of fuel. The basis for the design was a much larger basis, as we started out saying. We needed to have a reactor that they could use in this application, but it has to be economically viable at a much larger application. The reason I'm saying that is the Army doesn't want a $100,000 hammer. Okay, they want a reactor that is also viable in a commercial scale, for example, one of the large plants, so that they're made in large quantities, which makes them economically viable. So that's the target that we're using. And these would be containerized modules that would fit in here. As you know, synthetic fuels are going to be an increasingly important part of our future. for a variety of reasons that we all know. There's going to be 2 scales of production. There will be the mega scale, as we mentioned, in Qatar and elsewhere, where there are very large plants will be built. And then there'll be a lot of distributed plants. They'll be focused on biomass and waste and some coal and some special opportunities like this battlefield plant. And microchannel technology can handle all of these, but in particular, the niche markets, the markets that will open up first that have the highest advantage and payback, we fit into those very well because they're small. I want to thank you very much for your attention, and I'd be happy to answer questions.
So that 8 gallon per day is the largest unit you've demonstrated so far?
Yes, that's the largest one we've run to date, yes.
How do you get the catalyst into the microchannel?
Well, the microchannels on the catalyst side are wide enough, and we use a particle size that's appropriate for that channel. And we have developed some semi-automated technology. The channel, the top of the channel, you can imagine, is a long, thin slit. And so we have a device that sits over that little slit, and then you can slide the catalyst in.
So you have to disassemble it?
You have to take the top off.
How often do you change it?
Well, we change it when it needs to be changed. In this particular device, we changed it out once. The expectation is that in a commercial plant, the catalyst would be in there for years, at least a couple of years. And that you could, in fact, remove, in fact, that's what we're thinking, that you would remove the device, and you could take the device back to a location nearby where you could take the catalyst out. In our laboratory, we have a device to flip the reactor upside down so you can get the catalyst out more readily.
Thank you.
Regarding the reactor, 2 questions. Typically, in the tests we have done, what has been the pressure drop in this reactor, and have you seen an increase over time? The other one is you made a comment about the fact that you think capital cost of this reactor is likely to be lower than traditional reactors. Given how intricate the design is, how confident are you of that?
Okay, well, on the capital cost, obviously, since we haven't built and sold commercial units, it's all calculations at present. One way you can look at it, though, is based on the most important thing in there is the metal. If you can use the metal more efficiently and not have to put in too much extra expense into the construction, fabrication of that, then you can have it a capital improvement. And we, in fact, use the weight, the mass of the reactor much more effectively than a conventional reactor. So the fact that we have to put in more machining, if you will, to get to a more complex reactor, it's partly offsets the advantage we get from having a much smaller reactor. And the other the pressure drop. The pressure drop in this reactor that we're running is about 25 pounds through that 40-inch or 30-inch flow channel.
And that's
The SMR?
That's on that. No, not on the SMR. On the FT.
If you look at a size of an overall gas to liquids plant, and the idea of trying to make these small for locations and portable, moving them around, you've shown that you can make the reactors small, but how are you dealing with the ancillary equipment? That's still very big. Are you looking at making that small?
Well, some of the ancillary equipment, for example, compressors and so
Yeah.
on, are available small. In fact, they're available in great quantities, small, fairly cheaply. It's really when you have a gigantic plant that you have purpose-built
Right.
compressors. So there are a lot of components that are available at the scale that we need them, if they're components, without any trouble. The manifolding of the devices, as you saw, what we try to do is string several together so that they replace, if you will, in a tubular reactor, a bundle of tubes or several bundles of tubes. So you can think about it as if there's a bundle of tubes that you're replacing by this smaller reactor.
But still, you've got separators and all these other things around the reactors.
Well, those won't scale down
Yeah.
linearly, of course. You know, that's one of the reasons people go to larger and larger scale. But the most expensive components in a syn fuels plant one is the steam reformer. Right, that's probably the largest one. And the FT unit is another very expensive one. So on those pieces, at least, when you go to smaller scale, we get a significant advantage since our technology scales close to linearly.
Is this, a couple of questions. Can you tell us the particle size of the peppers you're using, and how you plan to scale out? You just mentioned that the pressure drop for half a meter length is like 25 pounds. When you go to higher and higher capacities, that pressure drop will be much higher, which will hurt the process.
Well, the pressure drop will stay the same because that is our commercial length. It's not going to be a longer bed. So the pressure drop through that same length should stay the same. As far as the catalyst particle size, we're still optimizing that a little bit. Typically, it's, I'm not sure I'm supposed to say, so I better not say, but it's smaller than the channel.
Are you using a cobalt-based catalyst or?
Yes, we're using a cobalt-based catalyst. Oh, okay, yeah, you did.
In the early days when losses of clean air give the top on this reactor, I think we talked about the water coating certain catalyst on your surface. So is that only limited to your SMR, and for Fischer-Tropsch, you abandoning that approach, you're going to pack in the dry particles inside the channel? Is that the conclusion now?
For Fischer-Tropsch, you can pack the particles in the channel because the heat release from a packed bed is not so high.
Yeah.
And so by using the appropriate size channels, you can get the heat out reasonably well.
Or did you expect after a few years, because of wax or stuff that your catalyst may be glued inside and you'll never be able to replace the catalyst?
No, I don't think that will happen. In fact, one of the things that is different about running these reactions in a microchannel reactor is that our linear velocities for our gases are considerably higher than they are in a conventional process. And that's one of the reasons that we get better performance, quite a bit better performance. Because if you think about it, this gas is flowing over the wax-soaked particles. And the faster that gas is flowing, it thins out that coating of wax and can actually move the wax out much more readily. So that's,
like you have 20% single yield there. But
it was about 15, yeah.
15%, that's significantly higher.
That was in that particular reactor. In our laboratory, smaller laboratory reactors, they're 9, 10, 11%.
What's the alpha value of wax did you use?
0.9, 0.91. Depends on how we run it exactly. It's pretty good. Pretty good. You had another question I forgot about the about the SMR. On the SMR side, there the contact time is much, much shorter. And so there, since there's a much higher heat transport, we use a coated catalyst, not a packed catalyst.
And how are you going to replace that? Like after a few years, because any catalyst after a few years, you have to replace it. You cannot simply tinker away. So you can re-wash coat in situ in the plant? Or
There are a variety of ways to regenerate the catalyst. That could be one of them. Or, as I mentioned, one of the things we're thinking about is taking the reactor out, replacing it with a fresh one, working on the old reactor back in the laboratory or back in our catalyst facility to do that, where you have more freedom to do things to a reactor.
What is the linear velocity that you can attain with this?
In the steam reformer, it's very, very high in
Yes.
and I'm sure I'll give you the wrong numbers, so I'll wait. I can probably find them out for you later.
That's fine.
But it's much higher. It's probably 10 to 50 times what it is in conventional process.
Yes,
Are you using an oxide diffusion barrier to prevent the migration of iron to the cobalt or vice versa, or is that not an issue at all?
It hasn't been an issue at all.
What is the current use of this synthetic fuel?
Pardon?
The current use, where we use it? Synthetic.
The current use of synthetic fuels? Well, I think Sasol, South Africa uses synthetic fuels for a lot of their diesel fleet. Maybe she could tell you more than I could.
More question? I think we have time to take a couple because we have only one paper after this. If it doesn't conflict with your schedule. Okay, go ahead.
Is this air person, or do you have an air set for this?
I'm sorry.
For the syngas generation, is it
Yeah.
air direct, or do you have a air set unit with oxygen in this small
No,
scale?
we're doing steam reforming.
Oh,
Steam
right, okay.
and natural
Yeah,
gas.
sure.
And on the other side, the combustion is air and a fuel.
What coolant do you use to remove the heat in the fish float reactor? Do you make steam or what?
It's steam, yeah. We feed a,
Boiler feed water?
pardon?
Boiler feed water to make steam?
It's steam, yeah. Boiler feed water. Yes.
Yes.
Just quick question. As you try to sort of commercialize this, one of the issues always is how would this reactor, this arrangement recover from upsets? What is the history of microchannel type reactors in terms of, for example, in Fischer tropes, I can see something where if you have a temperature upset, you're going to get a lot of wax plugging all over the little channels. Have you given that some thought, or is there some knowledge of how to deal with those situations?
Well, we're developing that. In this 1,200-hour run that we just did with the larger device, we did in fact have a few upsets in that, and we recovered from them all right. We're learning how to do that, how to regenerate the catalyst. As I mentioned, at the end of the 1,200 hours, there had been some slight decline, and at the end of the 1,200 hours, we were able to go back and regenerate the catalyst in situ, in which we didn't take anything out. We did it in situ. And the activity came back. So we're learning little by little how to do that, and we believe it can be done without too much difficulty.
I have a question. Methane selectivity is about 15%?
In that reactor, remember that was our first scale-up reactor.
So
In the laboratory devices, it's somewhat less.
Yeah, but in the commercial scale, the biggest scale is going to be around 15%.
No, I think in the commercial scale we'll do a little better. There were some,
Let's say 10%.
let's say, defects in the way that was
Are you
fabricated.
going to recycle it back to the steam reformer?
That depends upon the flow sheet that people have in mind. I think in some cases, yeah, it'll get recycled back to the steam reformer, or it could get recycled back to be fuel for the steam reformer,
Okay.
depending on what else it's mixed with.
Any question?